So we're talking about the Ronchigram. I'm still having my coffee break here. I don't want to mess it up, so I put it away. Okay, cool. So on Google Colab, again, you have to run that version to install all the different stuff. So we want to okay, I definitely have to restart that here. So we restart the server and run it. So the problem, why it takes so long on your computer and mine, is that it recompiles pytemlib every time, or the other ones are actually pre-compiled usually. What do we want to do? We want to understand how the apertures form the probe, and that's actually a little bit counterintuitive, because usually you would think the smaller you make the aperture, the smaller your probe is. But that's not the case. And we also want to see how the aberrations actually can be made visible in the Ronchigram, and how we then use the aberrations to change, to know what kind of beam shape we have exactly and beam size. So if we have an aperture, and that is what we had before, and everything is ideal, then we have no phase change. So it's completely coherently illuminated. Then all we have to do is we go in reciprocal space, make an aperture, and do an inverse Fourier transform, go back to real space, and that's what we have. So that means the larger we are in reciprocal space, the smaller we are in real space. So the microscope in STEM mode is the spatial resolution depends on how large of a space, of a coherent circle you can form in the Ronchigram that you then use with your aperture to make it small. Let's check it out. So if we have here 3 small aperture, and then you can see what happened. We get this from the area function, we get actually this reflections from the rim of the aperture, and they're very profound because we have a lot of rim compared to the inner part, right? So we have these oscillations here on the tail. Now, if we open that up, morning. Super. This is the same problem. Okay, that solves it sometime. So we open that up. That means we get more electrons in there. That means our probe is more intense. And we get less of a tail. So we are now at 10, then 30. That's where we were already, right? We get now a super intense probe because we opened up the aperture. That's actually exactly the same thing in the semiconductor industry, right? So they have this large aperture illumination that enables your, together with a very small wavelength, that is what enables this 3 nanometer pop. But the key thing is you get less oscillations, less tails, also less oscillations in the tail of the probe, and the probe becomes more and more intense. And so we already are moving into the territory where we have it pixelated by my Fourier resolution, so the resolution in Fourier space. And of course, because I know my 1/nanometer here, I know how big of a change I have here. The key thing in a modern STEM microscope is not so much the resolution anymore. So we have more resolution than we need. But what we really get out of the aberration correction is contrast. We get very intense beams that are very, very small. And so our images don't, when we are on the microscope or on the remote computer and access them, there is no image analysis necessary anymore to really see directly what you got. So the key thing is we're past where we need the resolution, but we really want the contrast in our images. And so we want to have as large as possible of a coherent illuminated aperture. So this limitation is called diffraction limit. And the other thing that we have to think about it, we can, of course, be only as small as the demagnified source size. So that are the main contributor to your part. And we already looked at that, right? So the Ronchigram is looking with a convergent beam at the reciprocal space, so diffraction plane, so the back focal plane. And if you defocus that, we also saw that already, we have a shadow image. So we moved in between the image plane and the back focal plane. So we need somehow get a very large area in reciprocal space where we can place our aperture on top. And okay. So that's what we're trying to do. We have our aberration function. That's our Fourier coefficients that we had before. We got them by the Semlin tableau. In the last notebook, since we have it up here, there was a question about it. How do you we had it somewhere. Oh, I thought it must have been further. No? Was it here already? Ah, okay. Aberration function. Yeah. Anyway, I had it somewhere. I put the paper of Semlin there, but I also highly recommend this book from Rolf Erni, Aberration Corrected Imaging in the Transmission Electron Microscope. Everything you need to know about how to do that with the Tableau is in here as well. So we make this aberration function. What do we need? So we have our aberration coefficients here. And if it's not in here, we put it to 0. And we have the first sum term, right? So that was the angular dependent term. And then we have the second sum. So that's the sum over all the aberrations of the sum and the cosine of the different angles. We provide this for the function by just a mesh of all the phis and thetas available. And then we want to calculate this Ronchigram. Let's go and do that a little bit further. So what we need is for the probe later is our aperture. And an aperture is very easy. So we put everything to the whole area to to 0, and we mask everything with an angle that is larger than our aperture and puts it to 0, right? So that's the only thing we let through is the aperture angle. So everything else is 0. It's a bit easier to see once we do that. So we have a field of view. We put some aberrations in here. It's an uncorrected microscope. And then if we are in reciprocal space, we have to go and get the intensities out. So the intensity in this Ronchigram pattern is just defined like any intensity of a wave. So I thought I've missed something here. So what we do is we go through an amorphous material. We have here our aberrations. So I have a defocus value. Everything else is more or less 0, but my C3, so the spherical aberration, is relatively bad. So an uncorrected microscope has it as spherical aberration of about 0.5 to 2.5 millimeter. If you remember, with our aberration corrector, the third orders were supposed to be better than 500 nanometers. So few orders of magnitude better with that. And if we change the aberrations around a little bit, so this is approximately where we want to be. Okay, we'll do that later. So it looks like a Ronchigram already. So this is something you would see on an uncorrected microscope. And all it is really is the wave in reciprocal space and with the aberration correction, and then folded with an amorphous material, which just is a random point here. We have then an aperture that we would want to set. That is the inner part. And you can see this is the 30 milliradians, the outer one. The inner one is 10 milliradians. So an uncorrected microscope, you can get to about 10 milliradians of a probe-forming aperture. It's not perfectly in focus. You see, we have a lot of features still in here, so we have a little bit wrong of the defocus. But what we definitely see is we have lots and lots of features here between 10 and 30 milliradians. So if you put 30 milliradians on an uncorrected microscope, you will actually get a worse probe than what you would get when it is nicely corrected, or even if it's smaller and you choose it correctly. So choosing the probe-forming aperture correctly is the key thing that we need to do, and that is what the Ronchigram helps us with. Okay. If we Ronchigram here, the whole thing together. Let's go back. I was playing around with it, obviously. Let's get that smaller. So this is nicely in focus. So you see it's more or less homogeneous in the center. Maybe we go a little bit smaller. Ah, yeah, okay. So this, you see, we have a little bit too large of an aperture chosen here that we would want. And we have the different parts. If you have now astigmatism, we can just play with that, right? You very clearly see this distortion in the one direction here, right? Let's do it with negative. Everybody can already check what they think it should happen. But the negative one is just 90 degrees to that. And we have another one that is 45 degrees to that. So if we zero that out, or at least make it small, that means your aberration corrector has very, very clearly defined directions that you can use. And so you can actually be sure that, say, whatever you calculate has, at least with a single rotation, is back to where you want to be. And most of them are directly related to your scan direction, right? So that's part of the job of the alignment from the company that you get the microscope from. Only in very unlucky cases do you have a 180 degrees change here. Okay, so aberrations. Let's put some sarcoma in. That's maybe it's not enough. So you see it's kind of bowed out in one direction here. It's not enough. Let's make it a little bit more. Okay, that's probably too much. No, doesn't change anything yet. And the third order should make it more triangular. It's a lot of, yeah, okay. So I really messed it up with that one. Okay. Anyway, so one can play around with it and can double check on what kind of, yeah, now we have our nicely triangular part here. So that is a threefold astigmatism. So instead of having it just like an egg, you have now this triangular distortions. Can everybody see that here? Right? So we have this triangular distortion. If we go on our microscope, all these people still here? Okay, they're still on there. Probably can see them. Where's my probe? So this faceplate here shows you how big of an aperture you can put in there. So this is what we saw, and I was just showing that. So now you understand, okay, this is the biggest one you can have in there. 35 milliradians. We usually go to at least 35 milliradians in the morning. By the evening, even if it degrades, we still have for sure our 30 milliradians that we have on the microscope, that we use as our aperture in that case. So you want to be always larger in case some thing happens to it. So let's go back. I think we need to lower our aberrations here a little bit. Makes it a bit more roundish for the faceplate. So this is the faceplate. This weird stuff, they obviously by CEOs they blocked it out, but the faceplate itself is just a Ronchigram without any kind of amorphous material in there. So on the microscope, when you go and you want to acquire a Ronchigram, you have to be at something that is very thin and very amorphous. The amorphous part of formware is perfectly nice and good. So the magnification in the Ronchigram is something interesting, because if we defocus it, we actually see that the inner part of this Ronchigram is an image. It is actually a high-resolution image. And if we go and look on the outside, this is also an image. And this image has a very weird behavior, and that is that the magnification changes as you go away from the center. So you have basically two kinds of centers here. And in the defocused one, you get this wheel-like structure. And that's what we want to look at in the next part here. And that is basically Andy Lupini's PhD thesis. He figured out that the Hessian matrix and the magnification are directly related. So the double differential matrix is what gets you there. And then you have two defoci. You have an axial one, that is the yellow one, the outer one. That is the axial infinite magnification. And the spoke-like stuff is the radial infinite magnification. So you have two infinite magnifications here in this Ronchigram that is defocused. And if we have an astigmatism, the defoci collapsed, right? So they were getting egg-like, and that's why you can directly see that. So if that is round, your astigmatism is corrected. So here we have no astigmatism. Geometrically, there is actually a relative interesting way of doing that. So we are in strong underfocus, and I made an animation here. So we have here the sample and our lens, and the ideal rays go, of course, to the focal plane. You know, we have our rays. But if we have now rays that are further out in the lens, of course, I mean, it's overdone here, then we have the focus 0. So we have perfectly focused, so infinite magnification. No, it's not quite. So I shouldn't have zoomed in quite as far, right? So we have infinite magnification directly here. And that is due to our spherical aberrations. So we have a direct measure for our spherical aberration with defocus. And so in the Ronchigram, we see that as the spoke-like pattern, right? So it's rays that are normally close to the in underfocus. So normally our beams cross exactly at the position of the sample. We go in underfocus. And so here we have an underfocused image. We have infinite magnification. And then the axial circle is actually even worse, right? So we have that in the center. And that gives us the outer ring that has the axial radiation, infinite focus. So this is how we can define that, and the infinite magnification rings here are directly related to our absorption, our aberrations. What actually Andy Lupini did, he went to a much lower underfocus so that the inner part is larger. And then he could show that that has also a relation to the magnification within that Ronchigram has a direct relation to the aberration function. And he calculates from one Ronchigram, different parts of this have different angles, and so he could go back and calculate the aberration function from that. So we now know the geometric part of that, and if we do that for the whole aberration function, which is of course relatively complicated, and then we have much more complicated change in the magnification. So our 0 points are a bit more problematic. I put them all here. So if you really want to do your mathematics skills and see whether I made a mistake somewhere, I would appreciate that, right? So we can load the magnification from some source. And, oh, shoot. That's not what I wanted to do. Where is my Ronchigram? Mm-hmm. Okay. Here's the Semlin tableau. I'm not sure whether we have the microscope open or not, but I loaded already some. Okay. So this is the weird, I think that was a neon at 60 kV. So that is the weird phase plates that we get there. I wanted to go and look at our microscope as well. So at 60 kV, of course, the aberrations are a little bit harder. You can change the defocus. And you can see already that on that aberration corrected microscopes, the angles are much larger, obviously, right? And it's not really anymore clearly defined what is an axial and what is a radial infinite magnification. You can see it a little bit here. So this is clearly spoke-like, right? But spokes is kind of problematic. And then here we have our radial ones, axial ones. And we have, of course, the infinite and magnifications that we can do by setting the Hessian matrix to 0 and see where that is exactly on our Ronchigram. And that is only that part. So what is radial, what is axial? That is very, very hard to distinguish. In this case, at least, that is the one where one cannot really do that. However, there is a trick to that. What you can do is, in anything that is a diffraction pattern, you go to polar coordinates, angle over distance, right? And if you look at angle over distance, then it looks much, much clearer. So you have the radial ones here, and here the axial ones. So it is actually, and here you have a weird mixture of them too, so you cannot discriminate them. The trick, however, is something you always should do when you do a diffraction pattern. Think about it in polar coordinates. So distance over angle, and so this is our angle, and that is the distance from the center. And you can do that on the image then, and you see how these two different solutions are separated out. So we have our Ronchigrams. What we do need to do next is we have to get back to the probe. In this case, it's defocused, obviously, right? So we focus the probe, get a nice shape, and then we set the aperture in the, you not see, okay. We set the aperture. We have an ideal one that is dependent on whatever aberration you have limiting. On ours, it's not longer C3. So in our case, it's hopefully C5, 0. So the fifth order rotational symmetry aberrations. In an uncorrected microscope, depending on your C3, you are in the order of 10 milliradians. In the corrected ones, you're in the order of 20 to 50 milliradians, depending on how well you did that. So how do we get to the probe shape? We have our Ronchigram, put our aperture on top. Everything outside the aperture is 0. And we make an inverse Fourier transform. So we don't do anything else. Where am I here? Probe shape calculations. We don't do anything else than here, except that now we have 30, right? Except that it is now not 0 everywhere, but a relative complicated landscape, right? And this residual aberrations that we have in the center will make it non-ideal. But that's all really that we do. So we go back, probe shape calculations. We make the probe by just making Fourier transform of that complex function. So what is the effect compared to the 30 that we just had? We have not perfectly round probe. It's a little bit off, right? It's a little bit larger than what we had with the ideal one. And our tails are a little bit larger. So go back. So it is these tails that we have that are larger, and they are introduced by our aberrations. The better the aberrations are corrected, the better it is, right? These aberrations are at 60 kV, not so bad. What is our full width of maximum? Okay, so this is in nanometers, so it's about an angstrom and a little bit probably. We do it all together. We can do the aberration correction. You can see now in the Ronchigram, it's not perfectly zero, right? So we have some amount of shapes in there. That is the same stuff that we saw in the in the calculations, and it gives us, this not perfect probe, but of course we complain on a very, very high level now, right? If you're talking about a 50 nanometer probe with a little bit of a wrinkle here and there, you can, but you need to know what you got in order to definitely see, especially if it's something that is a bit closer together and you want to get to the information limit instead of the correction. So if I see all the aberrations that I had from the microscope, if I had more time, I would just run a Semlin tableau. I get my aberrations from the microscope and can run all the rest of it. So I load the ones in here. So we have, so these are the ones that I had a few months ago. No, get me. Relatively nice and round, not too much of a problem, right? So with a little bit better aberrations, we got rid of these tails. So conclusions. Oops, where are my conclusions? I forgot to make them. What do we have? So we can, of course, all work together on that. This runs in Google Colab. There is no problem with that, except of the, you can copy. I'm not sure whether the copy and paste part works, but I have put a few standard aberrations from the different microscopes on there. They can check out the different probe sizes that you get. So it's very important to keep track of the aberrations in your microscopes, and you can get back to your probe size. You have to check at some point or the other how the probe size is related to your scan directions. Now that we all have gone through that, how would you do that? What is the simplest aberration that we can recognize? The astigmatism. So you introduce a little bit of astigmatism and you see in which direction it smears out, and you know exactly how that is related. Most the Semlin tableau is of course related to the scan direction itself, right? So we scan, we tilt, but we scan always in the right direction. So in our case, we never have a problem with that because the aberrations are directly related to our scan directions. If you do it with a Ronchigram, there might be a slight problem with rotation, but you can just double check that really quite easily, right? So no problem with that. And it is the tails that you can introduce with a bed. So the center is in an aberration corrected microscope normally quite nice, right? But if you have tails and you have atoms that are close together, then they change the intensity because two tails on top of each other or will move things around. And so they can lead to, in not too few cases actually, to confusion of what you find. But it's always good to do it as good as you can. So we need our aberrations. And if we look back to this one, to the GUI, let's go back to the bottom of it. Actually, we just take the aberrations and calculate the probe size, and that is exactly the same thing we did there, we do here. So we have some kind of astigmatism in the B direction, right? It's 45 degrees. And before it corrected it, and that's where it stopped. So we can use that, and we should use that in our microscopy. And the better the microscope is aligned, the better. Might not change too much on your images in terms of spatial resolution, but it gets you to a higher contrast, and that's what you really want. So you see more interesting features in your microscope. Okay, so let's see whether we have anything in the chat here. Okay, so this you can do it quite pragmatic. So I have the last one here. That was at 11. So that goes back to the question of how do you get the nanometer size quantification in the aberration coefficients with simulation. So we just did that, right? That's why I didn't answer it quite correctly in the beginning, but we just correlate that. We know how much it should change. And so we go actually backwards and forwards between simulation and the real image, and to also to quantify the aberration coefficient. It's the easiest way. You can do it more complicated, but then I would refer you to Semlin's paper and have fun with that. So, but it's very, very straightforward to do it just with the calculations of that. Okay. Good. Do we have anything else in the chat? One new message. When I correct the array, get an optimum probe. . Okay, so the who is that? Shantanu? Could you, there are two condenser stigmations on microscope. So one stigmation, actually there are three stigmators on there. So there is the condenser stigmator. There is the stigmator from the corrector, and the stigmator, a fine astigmatism corrector as well. So you basically have three different parts that you do, and you can actually make it worse by changing the wrong corrector. So what you should do is you change the condenser. Okay, I'll answer this question in a little bit. So, so you can change the wrong aberration corrector. What you should do is you should correct when you do the initial alignment, you use only the corrector astigmatism. And after that, in order to be able to set it back to zero, you should only use the condenser stigmators that you go in. And that should change stuff. If your microscope is not super well set up, and this aberration measurement is always to be taken with an error. So if you correct always A1 with 100% in the initial correction, then you will get an oscillation that will go down slowly, hopefully. So if you do that with about 75%, you will go down much more quickly. So don't trust it only to about three quarters. The microscope, in the microscope, the Ronchigram looks alive, right? So it kind of has this wobbly thing. And the question from Tao here is that where does it come from? And that is actually the temporal coherence of your source, so of your electron beam. So with time, your coherence changes, so it's stable for some amount of time. The microscope flies through your microscope, the electron flies through your microscope in, I don't know, femtoseconds. So it has to be stable in that part for getting a good probe. But over time, you see this wobbling. So it is actually, if it is changing too abruptly and pulsating, then you have some kind of electromagnetic problems in your room or on your system. So it should slowly go sideways, but it shouldn't go in and out or anything else. So you can actually check the status and the quality of the stability of the microscope without looking at this. The key thing is using the Ronchigram itself to monitor the health of your system. So there's lots of things to be done with machine learning and training. We have all the data in principle, right? So everybody is changing aberration corrector in the morning, hopefully, to get the resolution. So there are lots of different data sets. The point is to collect them. And as we will learn in the going on with this summer school, it's not only important to collect the data and make them available, you also need to provide the context. So what's been done, what has been found not to be good, why do you correct this and that? So we have provided with this GUI is that we have here a clear mechanism of how we do that. We show what is good and what is not good. And with that context, machine learning tool has much easier time to find that. And hopefully, maybe next year, we can show you how to do that in 20 seconds instead of 10 minutes, which is already quite nice, actually, for any kind of mind. So it is a temporal coherence of your flow. So check it out and make sure it's not working too much on our microscope. Are we over time now? If we look at that, so he is referring to the wobbling here, backwards and forwards. So you have two sources here. One is the coherence, right? How stable it is, and it is nice and stable. And the other one is the sample itself. So we have problems with the sample. Gold atoms sipping through. Sometimes you can see that when you're careful. But yeah, okay. So that much from the microscopy part. And once you have a good beam, you can just frost it over it and you get nice images. So we did that already. Thank you. Any other questions here? We don't have any. So, oh, there's another one in the chat. Okay. A nice column contrast. Okay, actually we can show the problem, but if you have a nice column contrast and one is off, then you have a problem with other aberrations, I would think. That sounds to me like B2, but without being on the microscope, this is very hard to judge. I'm sorry. So maybe we make a Zoom session once, okay? We can check it out. I'm not sure why you have said then. That sounds like other aberrations are getting in your way. Or your look at your Ronchigram. If that is okay, then it's good. So we can. Okay, if whoever wants to go to lunch is fine. I will just show you something. Let's go back here, and then let's do some astigmatism. Okay. Where are my panels? I need a left-hand panel. Okay. Let's do astigmation. Can you see how with the astigmatism you also change the magnification? Try that on your microscope. If that is not the perfect focus, then, so this is the normal behavior of an astigmatism in the Ronchigram. So you have this deviation, but you also have a change in focus because the disk of least confusion is moving out from the back focal plane, okay? You see here we have some images. They had the other one. Hiding. So I changed the astigmatism here as well on the multifunction ops. So that's how I change my astigmatism. Is as close as possible. So all of them change. So that gives me a good image, which I can see. In our case, this also will be, let's do it a bit slower. Okay. So yeah, we're back to where we were before. And the atoms are nice and round. And we have some scan here. Not sure where that comes from. Yeah, so we have some sample drift. You can see that it's not normal. So there are people in the room. You can tell. Okay,